Hello everyone. In today's video, we will see what are the different types of noise models used in digital image processing. The noise models are also known as the noise probability density functions or the probability density functions, and the principal source of noise in the digital images, it arises during the image acquisition and or image transmission, or just only during the image acquisition or during the image transmission. Now, during the image acquisition, the performance of the image sensor, it is affected by a variety of factors such as environmental conditions. And during the image transmission, due to the interference in the channel used for transmission, the noise will be added into the image. Okay. And the special properties of the noise, these refers to the special characteristics of the noise, and the frequency properties of noise refers to the frequency content of noise in Fourier transform. So the probability density functions PDF, it defines the probability distribution of noise in an image. And here we'll discuss the 6 most common PDFs in image processing applications. That is the Gaussian noise, Rayleigh noise, Erlang or gamma noise, exponential noise, uniform noise, and the impulse or the salt and pepper noise. So here this is the diagrammatic representation of the 6 types of PDFs which we'll be dealing with. First is the Gaussian noise, which is also called as the normal noise. And these Gaussian noise models, these are frequently used in practice because of its mathematical tractability in both the spatial and the frequency domain. That is, tractability means how easy something is handled or solved or managed. Okay, that is, it will be very easy to solve. And the tractability, it is very convenient, so that it often results in the Gaussian models to be used in situations in which they are marginally applicable at its best. That is, the Gaussian models are easy to work with, and people prefer these models because these are very easy, and easy even though when they are not the best fit for the data. So this is the formula for the PDF of the Gaussian noise, where Z is the intensity, that is, it represents the intensity. Z bar is the mean value of the variable Z, and this Z is nothing but the random variable. This is the PDF of a Gaussian random variable Z, and here Z represents the intensity, Z bar is the mean value of Z, sigma, it represents the standard deviation, sigma square is the standard deviation squared, which is called as the variance of Z, and this is the probability density function figure. So when this random variable Z, it is described by equation, this equation, then approximately 70% of its values will be in the range Z bar minus sigma and Z bar plus sigma, and 90% will be in the range Z bar minus 2 sigma to Z bar plus 2 sigma. Here we are taking a test pattern which is used to illustrate the characteristics of the PDFs. So this is just a simple image which we are using in order to see the histograms or to know the characteristics of the PDFs. Now here this is the image. This is the image and the histogram after adding the Gaussian noise. Okay, this is nothing but the histogram of the image. That is, this was the original image. After adding the Gaussian noise, the image has become like this, and the histogram for this is in this way. Okay, then next you have the Rayleigh noise, where the PDF, that is the probability density function, is given by this formula. Then mean is Z bar is equal to A plus square root of pi B divided by 4, and variance is given by this formula, that is sigma square is equal to B into 4 minus pi divided by 4. And here this is the probability density function of Rayleigh noise. Here there is a displacement, okay, from the origin, and the basic shape of the density, it is skewed towards the right. So the Rayleigh density, it is useful. It is useful in approximating the skewed histograms. So this is the figure after adding the Rayleigh noise, and this is the this is the histogram for the Rayleigh noise after adding the noise to the original image. Next, you have Erlang or gamma noise. This is the PDF, that is the probability density function, and here this is the mean and this is the variance. Here a will be greater than 0, that is it will be a positive integer, this a, and this exclamatory mark, it represents the factorial. Okay, and this is the probability density function, and here when when the denominator here, okay, when the denominator uh, is here, if it is rho into b, then it is called as a gamma density. Okay, that is this is the, that is here when the denominator, this denominator, it is rho b, it is called as gamma density. That is when the denominator in the gamma function, it is not is in the gamma function, is a rho b, it is called as a gamma density. And when the denominator it is as shown in this formula, then it is called as the Erlang density. Okay, that is the difference between Erlang and the gamma. If this denominator is rho b, then it is the gamma 1, that is the gamma density. If the denominator is like b minus 1 exclamatory mark, then it is nothing but the Erlang noise or the Erlang density. This is the probability density function for the Erlang or the gamma 1 gamma noise, and here this is nothing but the histogram stretching for the Erlang noise. Okay, this is after adding the noise, and this is the histogram for the Erlang noise. Then next is the exponential noise. So here this is the formula for the PDF. Then you have mean and variance. This is the probability density function, and this is a special case of the Erlang PDF, okay, with b is equal to 1. Okay, previously in Erlang you were having factor b. If that is equal to 1, then it becomes the exponential noise. And this is the figure after adding the exponential noise, and this is the histogram. That is, you can see here you are getting the exponential. Next is the uniform noise. So uniform noise, this is a PDF for the uniform noise, this mean, variance, and this is nothing but the probability density function. This is the figure after adding the uniform noise to the original image, and this is the histogram. Next comes the impulse or the salt and pepper noise. So here this is the probability density function for the salt and the pepper noise. Then here if b is greater than a, okay, if this b, if it is greater than a, then the intensity of b will appear as a light dot in the image, and the level a will appear as dark dot. Okay, if b is greater than a. If either pa or pb is 0, if either of these two is 0, then the impulse noise, it is called as the unipolar. And if neither of the probability is 0, that is if they are approximately equal, then the impulse noise will resemble the salt and pepper noise or the salt and pepper granules, which are randomly distributed over the image. And here the salt and pepper noise, it is also called as a bipolar impulse noise. Why? Because of this reason, because you will be having like small granules which will be distributed over the image, that is, you will be having some black dots and the white dots, because of which it is called as it is also called as bipolar impulse noise. Okay, salt and pepper noise, it is also called as bipolar impulse noise. And the other names for this is data dropout or the spike noise. This is the probability density function for the salt and pepper noise. And here when you add the salt and pepper noise, you will get this type of image. Again, this is the histogram. then. So here these noise impulses, what here these are nothing but the noise impulses. These noise impulses, these may be positive or these may be negative, and scaling, it is a part of the digitizing, that is a image digitizing process. And as impulse corruption, it is usually it is very large compared to the strength of the image signal. So the image or the impulse noise, it is generally digitized as extreme values. That is, it may be pure black or it may be pure white. And because of this, the assumption usually here is that A and B are saturated values, in the sense that they are equal to the minimum and the maximum values, which are nothing but the allowed values in the digitized image. Okay, and here, because of which we will get negative impulses which appear as black, which are called as the pepper points in an image, and even we'll get the positive impulses which are called as like which will be represented as white, that is nothing but the salt points. Okay, white points are nothing but the salt and black points are nothing but the pepper. So for a 8-bit image, you will be having A is equal to 0, which is nothing but black, and B is equal to 1, that is white. Now the Gaussian noise, it arises because of the factors such as the electronic circuit noise and the sensor noise, which are due to the poor illumination or because of the high temperature. Then Rayleigh density, it is helpful in characterizing the noise phenomenon in the range imaging. And exponential and gamma densities, these find applications in the laser imaging. Impulse noise, it is used in or it is found in situations where quick transients such as faulty switches takes place during the imaging. And uniform density, it is the least descriptive of practical situations, where but it is useful as a basis for numerous random number generators and generators which are used in the simulations. Okay, so this was about the noise models in the digital image processing. Thank you.